Early computers operated as straightforward, monolithic environments. A single program was loaded into the machine, and it assumed absolute, undisputed control over the entire system and all of its resources until it finished executing. Modern systems require a completely different architecture. We expect our devices to load a web browser, play streaming audio, and manage background memory simultaneously. To execute multiple programs concurrently without them crashing into one another, the operating system enforces strict compartmentalization. This need for isolation resulted in the concept of a process. A process is essentially a highly structured container. It holds the executable code, global variables, dynamically allocated memory, and system resources assigned to a specific program running in memory. Inside that container is the actual activity. The precise path of instructions currently being executed by the processor is called a thread. This diagram compares memory layouts. The left model has one thread, performing a single task. The multi-threaded model on the right performs tasks concurrently. Threads share code, data, and files, but each manages its own registers, stack, and program counter. Sharing resources makes multi-threading incredibly efficient, but sharing the data section introduces a massive architectural vulnerability. Because these distinct threads share a single memory space, they actively read and write to the exact same global variables. To understand why shared data creates execution collisions, we have to look at how modern hardware actually handles multiple tasks, relying on two distinct drivers: parallelism and concurrency. This chart details two approaches. On top, data parallelism distributes identical data across multiple cores to perform the same operation simultaneously. Below, task parallelism distributes entirely distinct threads across the cores, with each thread executing a completely different operation. But you don't even need multiple cores to run multi-threaded software. On a single-core CPU, the operating system manages this through concurrency. The process scheduler rapidly context switches the CPU's attention between different threads, interleaving their execution so quickly that they appear to be running in parallel. This is where the vulnerability lies. When these rapidly interleaving threads attempt to read and write to the exact same shared memory address at the exact same microsecond, they overwrite one another. The data becomes corrupted. Software alone cannot safely manage this traffic. True concurrent execution requires the operating system to utilize the physical physics of the hardware itself to prevent these execution collisions. To observe where high-level programming logic breaks down, we have to look down to the silicon. Consider a classic memory race condition. Two separate threads attempt to increment a shared variable simultaneously. Standard assignments fail here because modern CPUs physically reorder load and store instructions on the fly, causing the operations to overlap and the final value to scramble. To solve this, kernel developers rely on a foundational hardware solution known as a memory barrier or a memory fence. This forces the CPU to complete all pending load and store operations before it is allowed to execute any subsequent instructions. Preventing data corruption at this microscopic level requires a hard physical stop in the execution pipeline. Software instructions alone are insufficient to guarantee order. Moving one layer up the synchronization stack, operating systems rely on special hardware-level atomic instructions. When an operation is defined as atomic, it means it is executed entirely as one single, uninterruptible, and indivisible unit of work. A prominent example is the compare and swap instruction. Before allowing a new value to be written into memory, the CPU checks the current value against an expected baseline. If it matches, the swap is approved. If it doesn't, the operation fails and returns the original value. On an Intel x86 architecture, enforcing this atomic execution requires the processor to literally lock the system bus. It snaps the hardware pathway shut, physically blocking any other processing core from modifying that memory location while the swap takes place. Operating systems use these atomic instructions to construct what is known as a spin lock. If a thread needs a variable that is currently locked, it enters a state called busy waiting, where it loops continuously, asking for access over and over again until the variable is released. But there is a strict efficiency rule for this design. Spin locks are only beneficial on multi-core systems if the lock is held for a highly specific duration, less time than it takes the processor to execute two context switches. If a resource is held for longer than that, a spin lock becomes a liability. It protects the data, but it wastes valuable CPU cycles, spinning uselessly in a loop while doing zero productive work. To solve the inefficiency of busy waiting, computer scientists developed a higher-level software abstraction, the semaphore. Introduced by Edsger Dijkstra, a semaphore manages access to a resource based on an integer count. Threads interact with that integer using two standard atomic operations, wait and signal. A semaphore utilizes an integer value and a dedicated wait queue. When a thread waits on a zero integer, the OS actively suspends it into the queue. When the resource releases, calling signal increments the count, waking a suspended thread back into the ready queue. Semaphores preserve CPU cycles by removing waiting threads from the hardware entirely. But by relying heavily on the operating system's scheduler to suspend and wake processes, this architecture introduces complex and dangerous new dependencies. All of these synchronization tools, memory barriers, spin locks, semaphores, exist strictly to protect the state of data. But implementing them guarantees a new risk, the possibility that a process attempting to enter its critical section will wait indefinitely. In concurrent programming, this is an example of a liveness failure, and the most notorious version of it is a deadlock. A deadlock occurs when a set of processes are waiting indefinitely for an event, like a semaphore signal, that can only be triggered by another waiting process within that exact same set. Take a system with two processes, 0 and 1, accessing two semaphores, S and Q. Process 0 successfully executes a wait on semaphore S. To finish its task, it then needs to acquire semaphore Q, so it waits. Concurrently, process 1 executes a wait on semaphore Q. To proceed, process 1 now needs to acquire semaphore S, which is currently locked by process 0. Process 0 is waiting for process 1, and process 1 is waiting for process 0. This creates an unresolvable circular wait. The system is completely frozen, not because of a programming error, but because both threads perfectly obeyed the strict rules of mutual exclusion. Deadlocks happen due to competing resource demands. But there is a different liveness failure caused strictly by the operating system's scheduling hierarchy, known as priority inversion. Assume we have 3 threads running on a system: high, medium, and low priority. Right now, the low priority thread is active, and it holds a lock on a critical piece of kernel data. Suddenly, the medium priority thread becomes runnable. Because of its rank, the scheduler preempts the low thread, pausing it to give the CPU to the medium thread. Now, the high priority thread needs to execute, but it requires that critical kernel data. It is blocked because the data is still locked by the paused low thread. By preempting the low thread, the medium thread has indirectly starved the high priority process, forcing it to wait indefinitely. To prevent this, operating systems implement an automated scheduling fix called a priority inheritance protocol. Under this protocol, any lower priority process accessing a resource needed by a higher priority process is allowed to temporarily inherit the higher priority. The OS boosts the low thread, preventing the medium thread from interrupting it, just long enough for it to finish using the resource and release the lock. Operating system design is a zero-sum balancing act. The more granularity you apply to protect the state of your data, the more overhead you must dedicate to complex scheduling protocols just to guarantee the system continues making progress.